Thanks. This is joint work with Kevin Liu, Alex Slivkins, and Stephen Wu. So the starting point of this project is this observation that online platforms increasingly engage in product experimentation, trying out different product configurations and different algorithms to learn what works. And so this problem is very well studied in isolation. What's a little bit less well studied is the fact that most of these platforms engage in experimentation while simultaneously competing for users. And so in this paper, we're going to look at a scenario where firms compete for users and simultaneously learn from the data generated by it. In particular, this leads to a trade-off. Can you read? Okay. Does this work? Okay. Yeah, it seems auto. So the thing that this leads to is this trade-off between exploration and competition. Where on the one hand, a firm needs to incentivize users to choose them over their competition today. On the other hand, they sort of need to make suboptimal decisions today and explore to gain information to have a better product tomorrow. And this motivates two broad questions. The first is, does this introduction of competition incentivize what we traditionally consider as the adoption of what we traditionally consider as better algorithms? And what are the welfare consequences of the algorithms that get incentivized? And the second is that in this scenario, in this setting, when you have firms that are learning while competing, what's the role that sort of data asymmetries between the firms can serve as market power and barriers to entry for an entrant into the market? And so to study this, we're going to start from the model that's been discussed by a couple of the previous speakers, the classic multi-arm bandit problem, which is that you have some finite number of periods. In each of these periods, you have a fixed set of arms to pick from. In each period, you select an arm. You observe a reward for that arm and nothing else. And the thing that makes this problem interesting is that the means of rewards of each arm are not known ahead of time. And this is very well studied since it captures the exploration-exploitation trade-off, where exploitation being is make the best decision today given the current information, and exploration being make a suboptimal decision today with respect to my current information in order to gather information to make better decisions tomorrow. And so in our model, we're going to have two firms. Each of these firms is going to face an identical instance of this bandit problem. You can sort of think of the k different arms here as k different ways of serving a user. At the beginning of the world, each firm is going to commit to a bandit algorithm that they're going to play throughout the game. And we're going to suppose that firms start with no initial information, so they have a flat prior. There's going to be a warm start of some exogenous T naught, which is going to be the number of rounds they make progress on their learning problem before competition starts. And so the way we're going to think about competition here is you can think of it, there's going to be a stream of users who arrive one at a time. In each round, a new user arrives. There's, suppose the firms are called firm A and firm B. The user, suppose, picks firm A. Firm A chooses an arm. The user receives a reward in accordance with the arm that they pull. And firm A observes the reward that the user experienced. And the crucial component of our model is that the reward is only observed by the chosen firm. So firm B gets no information if the user chooses firm A over firm B. And so here we're going to have that the firm's objective function is to maximize its expected market share. And in particular, we're going to have that user's choice is driven by some reputation score. So every time that a user picks a firm, that user is going to experience a reward. And the average over some sliding window of the rewards that are experienced is going to be the reputation score for the firms. And so a user is going to arrive and observe the reputation score of the two firms and pick deterministically the one that has a higher reputation score. And so we're going to sort of cast our model in this sort of relationship between innovation and competition. So we're going to we're going to utilize the distinction in the bandit literature between three general classes of algorithms. The worst class of algorithms are algorithms that only do exploitation. So generally greedy algorithms that pick the arm with the maximum mean reward. The second class of algorithms are these sort of exploration separating algorithms, which separate out exploration and exploitation into separate rounds. And the third class, which are traditionally considered the best, are these sort of adaptive exploration algorithms, which do exploration in a smart way. And so from the first class, we're just going to use a greedy algorithm. From the second class, we're going to use dynamic epsilon greedy. And from the third, we use Thompson sampling. So we pick representative algorithms from each of these classes because we only qualitatively care about which class of algorithms gets incentivized in equilibrium. And in terms of thinking about competition, we're going to vary timing of entry and the number of firms in the market. So the least amount of competition is going to be a monopoly case, where a firm is just simply there. There's going to be one firm in the market, and that firm is just simply going to get all of the users. The next level of competition is going to be a firm that sort of gets a temporary monopoly, which we call here an incumbent, where for some number of rounds, every user that comes in the market has to come to me, and I don't need to incentivize them to come to me, but that after some number of rounds, another firm enters, and then the user can pick between the two firms. The next level of competition that we consider is sort of this simultaneous entry duopoly, where two firms enter at the same time. And the most extreme form of competition is basically an entrant that comes into the market when there's already an incumbent. So when I enter the market after there's a firm that's been there for some number of rounds. And we're going to ask for each of these situations sort of what algorithms get incentivized. Yeah?
You previously said you were assuming a warm start where everybody gets T-naught
Yeah.
rounds of pre-exploration.
Yep.
Is that assumption made in each of the incumbent duopoly?
Yeah, so so let me go to the next slide. So we basically run a bunch of numerical experiments, and so we run a bunch of experiments varying that T-naught and looking at the results across those T-naughts. Okay, and since we study this via numerical simulation, we also have to we try to consider representative classes of instances so that the space of numerical experimentation isn't too large. So the first class is sort of a needle in a haystack where there's one good arm and k minus one identical bad arms. The second sort of disperses the arms a little bit more so that it's uniform over a quarter and 3/4, but here aren't arms that are very good or very bad. They're sort of dispersed in the middle. And the third class are sort of these class of bandit instances where there's heavy tail probability. So basically, it's very likely that the arms are either close to 1 or close to 0. And so each numerical experiment here is going to be competition between a set of bandit algorithms. So the parameters are a pair of bandit algorithms, a particular competition model, and the class of an abandoned instance. And we're sort of going to look for results that are consistent across each of these. And so in terms of the related literature, our work builds off the very vast literature on multi-arm bandits, which is sort of how we pick from to sort of pick the class of algorithms that we choose from. The more recent work sort of looks at bandit algorithms with incentives, as you could see from some of the previous talks. And the main idea here is there's sort of a principal who runs a bandit algorithm and generally myopic agents who are either bidders in an auction, users in a recommendation system, and a bunch of different scenarios. But the key here is that they control the information that the principal receives. And so in economics, the sort of relationship between competition and innovation is very well studied, going back to Schumpeter from the 40s, and the general theme that emerges from this literature is sort of an inverted U relationship, so that too much competition or too little competition are bad for innovation, where sort of intermediate amounts are good for innovation. And so in the context of exploration, there was earlier work by Alex, Stephen, and Yishai Mansour, which looks at a similar model. The main differences here are their model had no sort of reputation, so users had no idea about the rewards that were experienced by past users. They varied competition by user response model, so having random agents as opposed to timing of entry, and they looked at mainly asymptotic theoretical results, whereas here we look at we use numerical simulation to look at much more realistic finite time scales. Okay, and so before we jump into the results of what we found when we ran our numerical simulations, first we sort of studied, on the classes of instances that we looked at and the set of algorithms that we studied. We looked at the performance in isolation and sort of looked at what statistics were predictive of results we expected to see in competition. And so the first thing that we noted was that mean reputation was not necessarily the most predictive statistic for results in competition, which I won't talk too much about now, but you can look at the paper for more details. What we found was that a better predictor was a statistic that was much more natural in the context of our model, which was sort of this relative reputation statistic, which looked at, at a given time t, what were the fraction of simulations in which algorithm 1 had a higher reputation score than algorithm 2. And so if you look at I can't really point, but if you look at the bottom left here, you sort of see that there were two classes of instances. The first are basically these sort of exploration disadvantage instances so this graph here shows on the uniform instance, the relative reputation statistic of Thompson sampling versus dynamic greedy. And so as you would expect, you sort of see that there's an initial dip in Thompson sampling's relative performance because in the early rounds it engages in exploration, but that eventually it does better. But that, for instance, on the needle in a haystack instances, you don't really see this sort of behavior because exploration isn't as costly for reputation. And so we focus on these exploration disadvantage instances, and we sort of have the following sets of results.
So the first thing was that in the monopoly case, we suppose because they never have to incentivize users to pick them, they can just adopt the greedy algorithm. On the other extreme, when I'm a late entrant into the market, I have a dominant strategy to play dynamic greedy. In the intermediate case, when I'm a first mover, so I have I'm an incumbent and I have some number of free rounds before other people enter, I am incentivized to play Thompson sampling. And in the simultaneous entry duopoly case, sort of we get that dynamic greedy as a Nash equilibrium. So we'll go through these one by one. So the first is, why is it that in the duopoly case, we sort of have that greedy algorithms are incentivized in equilibrium over better algorithms? So what we do is sort of we track this statistic, which we call the effective end of game, which is the last round t, such that the agents at time t and times t minus 1 choose different firms. And so we sort of observed that whenever Thompson sampling was involved as a strategy, that there was a low effective end of game, in particular when warm starts were relatively small. So we interpret this as sort of indicative of a death spiral effect, where basically a firm engages in exploration. On average, this leads to lower reputation. This leads to fewer users. So that means that my competitor gets more users, so they get more data to make progress on their learning problem. And so they have a low relative reputation, and sort of this continually spirals until eventually the firm that engages in exploration gets starved of users completely. And so we sort of allow now that there's some staggered entry, so that there is a firm that enters the market early, and we sort of give it this temporary monopoly. And what we find is that the incumbent or the early entrant is incentivized to play Thompson sampling, whereas the late entrant is incentivized to play dynamic greedy. And so down here you can see an example of one of these induced games. So the way to read this table, I can't really point, but the row column is the entrant, the incumbent is the column player. No, thank you. Cool. So the row column here is the row here is the entrant, the column is the incumbent, and these numbers here are the average market share of the entrant. And so in particular, this is one parameterization where there's a 200 round head start on the heavy tail instance. And the first observation you can note is that no matter what the incumbent does, they get a relatively large market share. But the important thing here is that they're sort of incentivized to play Thompson sampling. And the intuition for this is pretty clear. So the incumbent doesn't incur the immediate reputation consequences of exploration, unlike in the simultaneous entry case. And as long as this temporary monopoly period is sufficiently large, they effectively only face the classic exploration-exploitation trade-off and pick algorithms that are best optimizing this trade-off. But they sort of still need to compete against a later entrant, and so need to do as well as they can by the time that the entrant enters into the market. And so we look at welfare across these different the equilibriums in each of these different games. And so our welfare measure here is a standard measure that's used in the BANDIT literature, which is just the regret accrued by all the consumers that have, or all the users that have been in the market. And regret is the difference between the best action in hindsight and the action that was the mean of the best action in hindsight and the mean of the actions that were actually taken. And so the first thing to note is that you sort of have linear regret for the duopoly and the monopoly cases, because the greedy algorithms are incentivized in equilibrium. Whereas for the sort of the temporary monopoly case, because Thompson sampling is incentivized for the incumbent and they get most of the market share, you sort of have this logarithmic regret. And so a natural question after looking at this is, okay, so in the duopoly case, we sort of restricted things to 2 firms. A natural question to ask is, what if we just increase the number of firms but have them keep playing the greedy algorithm? Does that actually lead to better welfare? And so we don't look at equilibrium behavior here. We just say, we restrict all the firms to playing greedy, and we increase the number of firms in the market. And we observe that increasing number of firms weakly decreases welfare, which sort of goes against the intuition that adding more firms in the market, even if they're playing greedy, maybe one gets lucky and finds the best arm, and that actually leads welfare to effectively go to 0. We don't observe this, and we actually observe that it doesn't make things that much better. So yeah, so welfare we define as the total regret incurred by all users. So again, basically in every round, a user is going to arrive. They're going to pick a firm. That firm is going to pull an arm, and so the 2 firms play identical BANDIT instances, and so you can sort of in every period, measure the difference between the mean of what the best action would have been in hindsight and the mean of the action that the firm actually gave them. And so, yeah, to note here that because we're using regret, sort of lower regret is higher welfare, in case that wasn't clear. Okay, so now let's go back to looking at the temporary monopoly case, right? So we sort of saw that that case led to the highest welfare, but something that's a little bit strange here is sort of, there's two advantages of early entry, right? So on the one hand, you have that there's a reputation advantage. So being early in the market sort of gives me a more definite and potentially better reputation. The second is sort of a data advantage, right? So I have more data than the entrant. And so a natural question to ask is we observe that the incumbent sort of has a large market share. Which of these sort of leads to that large market share? Is it more reputation or is it more data? And so we run two experiments. So the first is a reputation advantage only experiment where we reset the incumbent's information when the game starts. And the second is a data advantage only, which is we reset the incumbent's reputation when the game starts. And we find that either advantage alone leads to a large market share, and that the data advantage is sort of larger when the incumbent commits to Thompson sampling. And so again, the semantics of this table are the same as before. So the row player is the entrant, the column player is the incumbent, and it's using the same parameterization from the slides before. And so this table sort of looks at the results from the data advantage experiment. This looks at the results from the reputation advantage experiment. And so again, a striking thing to note is that no matter what, the incumbent still gets a majority of the market. And that if you look at the dynamic epsilon greedy and dynamic greedy payoffs, they're relatively similar across both experiments. But you sort of observe that for the data advantage, so note that a lower market share here basically means a higher market share for the incumbent. And so you sort of see that when the incumbent plays the Thompson sampling, they actually have a larger market share. Okay, so to sort of conclude, we could sort of consider the model of competition between learning algorithms. We found that sort of better algorithms were not always better in competition, sort of due to these reputational consequences of exploration. And finally, we sort of found that data can serve as a barrier to entry in online platforms, especially in reputation sort of has these reputational consequences.